In some earlier videos, I've talked about methylene groups, CH2s, that troublesome little bit of a molecule that can really give us some trouble when we try to interpret proton NMR spectra. They are prone to overlap. If they're on a terminal alkene, the lack of free rotation gives them different chemical shifts. And links to those videos will be in the description for this one. I want to push ahead with that because there are some really interesting examples of methylene groups giving us trouble that don't involve signal overlap or terminal alkenes. The other great source of methylene trouble, chiral molecules. So I want to show you two examples, one non-chiral, one chiral, and show you exactly how that can really affect the appearance of an NMR spectrum. The first molecule is going to be this one. I call it FMOC. It has some long organic-y name, fluoromethylene oxycarbonyl chloride. I don't know. I don't care. It's some biochem leaving group. And they call it fluoro because, of course, it has not one fluorine in it. And the organic chemists all love to tell us how systematic their nomenclature is. But I'm straying. So I want you to look at the proton NMR spectrum of FMOC, and it is quite a lovely, lovely textbook example of a spectrum. Here the aromatic section looks beautiful, and I want you to notice it has 4 distinct resonances in there. This molecule is symmetric. And then we look at the non-aromatic parts, the CH, the CH2, and we see exactly what we would expect to see. We see a lovely little doublet. We see, because of the CH2 group, the CH is right next door. We see a lovely triplet of the CH, because it has 2 protons right next door. If I were writing a textbook and I said, here's a textbook doublet and a textbook triplet, this would be the textbook example. But I want to take that a little bit further, and it deals with the fact that I said this is a symmetric molecule. I've had some students who will look at that structure and say, what do you mean it's symmetric? It doesn't look symmetric to me, and the way it's drawn, often it doesn't look symmetric, but it is critical to remember free rotation about single bonds. Now, the best way I know of to illustrate stuff like this is our dear friend, the plastic. I just love plastic. So I'm going to get a little bit closer to the camera, which is always, kind of a bad idea for me, and play around with the plastics. I'm just old-fashioned enough that I just love these things. All right, so here's a piece of plastic trying to illustrate FMOC. The white ones here are going to be the aromatic rings. I didn't construct the whole aromatic rings, I don't care. The reds here are the hydrogens. There's the CH, there's the CH2, and then back here the oxygen, the carbonyl, the chlorine, and they usually have it drawn where the chlorine group of the acid chloride section is over here someplace. And it doesn't look like it's symmetric, but remember, with free rotation about this thing, the question isn't which is the best sterically, which is the best configuration. The question is, in free rotation about single bonds, is there a configuration you can find? Oh, there's one that puts a mirror plane between, let me make sure I get that just as perfect as I can, between the protons of the CH2 group. And so there it is. And what I'll do is I'll actually hold it by the CH2 group here, a mirror plane. Now, is this the best configuration possible? No. Maybe not. I don't know. I could come up with some terrible looking configurations. It doesn't matter how likely it is. Is it a configuration that puts a mirror plane between the protons of the CH2 group? And in FMOC, I can come up with these types of configurations. Therefore, these 2 protons, the protons of the methylene, will have the same chemical shift. And if there's the CH, the chemical shift difference between these is quite large. So there's the CH here, causing these guys to be the doublet. There's the CH2, 2 equivalent protons, causing this guy to be a triplet. Everything is just perfect with this molecule. Like I say, textbook molecule. Terrible name. Textbook proton NMR spectra. The other molecule that features a CH-CH2 group is actually simpler than FMOC by quite a bit. It's an amino acid. It's asparagine. And here is its proton NMR spectrum, and I use it as, in my classes sometimes, as a beautiful example of, well, that doesn't look quite like I expected, and it doesn't. This is a much more complex looking CH2 group than FMOC had. We do not have a doublet and we don't have a triplet. We've got other things. Now, technically, we have a doublet, and we have actually sets of doublets here. I want to point this thing out here. This is actually the CH2 group. Sometimes students will look at that and they'll say, oh my, that's a quartet of doublets. Yeah. But no, it's not. And the reason simply is, remember, a quartet, the separation between all four peaks, the separation between all four peaks has to be identical. And if you look at this thing carefully, and especially if we put the numbers on it, you'll see that in a moment, and I'll make that available on the description as well, is the center peaks, there we go, are different than the outer peaks. Secondly, the doublet nature here. It seems that, on one side, the doublets are just tighter, closer together, not as well separated as on the other side. Now, these are actually two doublet of doublets. But boy, they look kind of funny. We'll talk about that in a minute. On the other direction, you see a much more textbook, if you will, doublet of doublets. It's quite lovely to look at. So what is it about this molecule that makes it so different? Well, once again, a piece of plastic to help us with this. So here we go. Here's the piece of plastic, and I've just got it configured this way for a moment. We have this CH, here's the CH2. I'll rotate it around so they're a little bit closer together and easy to see. And I'll do the same thing I did with FMOC. I'll let's see, let's get all this thing together, and we will go for the, wait a minute. I'm using the white and the blue here to represent the different components on the carbon of asparagine. And, there's not a mirror plane right there. Well, yeah, but okay, I know. Let's put this around this way. There, that'll get us the mirror plane, because clip. Oh, rats. Oh, it's these two stupid things. Okay, I know. We'll do that, and we'll put the blues and the red together. No mirror plane. Darn it. I know. Let's go. There we go. No mirror plane. The point about this one is, yeah, it's got free rotation. These bonds are all freely doing their thing. That doesn't matter. No matter what configuration I put this thing in, good ones, bad ones, doesn't matter. There is not one, as this thing moves around, that will ever put a mirror plane between these two protons of the methylene group. None. Why? Because that's a chiral carbon up there. And if you remember, the greater definition of chirality is not carbon with four different things on it. It's a molecule lacking a mirror plane. There is no configuration that puts a mirror plane in this molecule. Therefore, there is no way that these two protons, though they are on the same carbon, can ever be in the exact same chemical environment at the exact same time. And if that's the case, then these two will never have exactly the same chemical shift. They will always be different from each other. A chiral center causing the protons of a methylene group to have different chemical shifts. Now, that is what's responsible for the bizarre coupling patterns, or the, not bizarre, but the interesting coupling patterns in this amino acid asparagine. For example, this one, it's next to a CH2 group. It ought to be a triplet. But these two have different chemical shifts, therefore they are likely to have different coupling constants to this particular proton. This one will make it a doublet. This, with a different chemical shift, makes it another doublet. A doublet of doublets. Now, this one over here, this one, it will be a doublet because of this one back over here to the CH, the classic 3-bond vicinal coupling. But this dude over here, the geminal 2-bond position, if these don't have the same chemical shift, and they don't because there's no mirror plane in here, then they will have different coupling constants to each other. And so you're going to get a doublet of doublets from this thing. And the exact same story about this particular proton. So we have a set of doublet of doublets, doublet of doublets, doublet of doublets. Oh, it's just beautiful. Now, why is it a second order doublet of doublets for these two protons? Mainly because the chemical shifts are different, but they're not hugely different. If you have a chiral center here right next to the CH2 group, you'll often see this, the CH2 groups have different chemical shifts. Sometimes in cyclic molecules like menthol, it can be a whole ppm or more. Here, it's much smaller than that, but it is definitely measurable. Remember, you see your second order coupling patterns if the chemical shift difference between these two, which is small, and the coupling constant are on the same order of magnitude. Now, if this CH2 group were much farther away in a much larger molecule from the chiral center, then frankly, this effect diminishes as they get farther and farther away from each other in space. And so, in a chiral molecule, but with CH2 groups, far away, all the usual doublets, triplets, and quartets usually will appear quite normally. It's only when you're near the chiral center that things start to get a little haywire. And so a quick reminder of what I mean by second order effects again. If you have two signals split into doublets, so you have a doublet here and a doublet there, and they're far apart from each other, so like 2 ppm and 5 ppm, something like that, you're going to get two signals, beautiful doublets, everything will look normal. But remember, if the chemical shift difference gets smaller, and I'm just going to bring them together, what will start to happen is the outer peaks will begin to shrink at the expense of the inner peaks. And so for asparagine, you're in something like this, where the two outer peaks are definitely visible, but smaller than the inner peaks here. If you look at a related amino acid, aspartic acid, or aspartic acid, however the hell you pronounce it, I don't care. If you look at that proton NMR spectrum, and in fact, they're very hard to tell apart by proton NMR, asparagine and aspartic acid are, you'll notice that you see the same doublet of doublets going on with the CH2 group, but it's much more extreme. These two are even closer together. So the outer peaks have really shrunk at the expense of the outer peaks have really shrunk, the inner peaks have grown. So it's even more second order than asparagine, but neither of them is normal, quote unquote, like the FMOC was. And finally, I'll just make mention of my adoration for the plastic models. You could also certainly use computer graphics to do this sort of thing. I'm just old-fashioned enough that I like the plastic. The organic chemists will use their ever-beloved Newman structures to do this sort of thing, and that can be quite powerful as well. But for my money, give me the old-time plastic anytime. Just love these things. So there you go, methylene groups. Another way they can be quite problematic when you're trying to interpret a proton spectrum. The second order effects, the fact that even though they are on the same carbon, if there's never a mirror plane between them, they can never have the same chemical shift. They can have a close chemical shift, but not exactly the same. And despite all that free rotation going on, CH2 groups near chiral centers, another source of trouble for that simple, seemingly CH2 group. Darn methylenes, but we can handle it. And we see a few examples, and we move on from there. Hope you found this helpful, and we'll talk to you later.